Okay, great. So this is our CPP ball example that we've spent several lectures on. So we have here we have the default constructor. It's default constructor because there's no arguments. And we also have the parameterized constructor. This means it has arguments. We have a copy constructor. This takes in a reference to the same object, and then we copy it over. And then we have the assignment operator. And we talked about all the different ways to call each of these. Now, I began talking about, well, what if, instead of just having members that are created on the stack, what now happens if we have a pointer to an object? Well, what this means is now in order to instantiate this pointer, you probably would want to call new, right, when you create this object. So here for the default constructor, I just gave it a value of 8, and then here in the parameterized constructor, I gave it a value of 9. If I wanted, I could pull it in from another parameter. And then copy constructor, here, this is how I copied it over from B. So I took the value that was at this B dot pointer, and then I dereferenced it, and then I copied it as the new value. And then it's the same thing for this assignment overload. Okay, but anytime that we create new memory with new, what do we need to do afterwards? We need to free it. Yeah. Okay. And the reason for that is what would happen if we didn't free it? Yeah. Yeah, it's a memory leak. So in C and C++, it is one of the most difficult parts of C and C++ is managing your memory. Because anytime that, and it's very often that you want to use the advantages of creating heap allocated memory, but anytime you create memory on the heap, then now you need to make sure that there's something there to help you destroy it. And so what we can do is we can create a new type of method. Instead of a constructor, we now call it a destructor. So it's kind of like a constructor, except now we add this tilde. And then inside this, so now we can add a print statement. We won't do anything with it yet, but let's just see what happens. So we can call this destructor called. Okay, so this is our destructor. And let's now run this. So G++, CPP ball. Come on. There we go. Okay, cool. -o main, and then /main. Okay. So there you go. Okay. Well, here, we see 4 destructors called. That's kind of interesting. So let's just double check what our main is. Okay. So our main, we have created an object here, created an object here. How many objects are we creating? Just shout it out. We're creating 4 objects, right? B0, B1, B2, B3, right? We're creating 4 objects, and then we return. But we're not calling any sort of free or anything right here, right? So how does it know that the destructor should be called? Yeah. Exactly, yeah, we're exiting the scope. And on this return right here, that means that anything that we have created inside of the scope, specifically any stack variables that we've created on the scope, now we need to destroy them. Yeah. Watch what would happen if I crashed the program unexpectedly. What would happen now if I maybe did I don't know. Yeah, this is fine. So what if I now say instead of B3 equals B0, maybe after that maybe I say B3 equals, and then I just make you ready for this? Okay. Boom. Okay, so I take this value of 0 and then I make it a ball pointer. Except we should now, I guess, dereference this. Yeah, okay, look at this. This is nasty. So we're just taking this value, we're pretending like it's a pointer, and then we're passing it in. So now let's see what happens. So if we run this, then, okay, right? Program breaks, makes sense. But notice how there's no destructors called, right? So the memory is not freed by returning from the scope. So the destructor is an actual function that is run anytime that you explicitly delete an object. And when it's a scope variable, that member will be, that the object will be deleted when you leave the scope. And like similarly, if we now wanted to create like a ball object on the heap, so if I'm going to get rid of this. So if I now create like a ball 4, but we'll make it a pointer, right? And say it's equal to new ball. And let's just do this. What constructor will be called here? This will be the default constructor, yeah, okay. So we are allocating memory for this ball object, and we are putting it inside of this pointer b4, okay. And so now watch what would happen. So right, so we're now, how many objects are we creating here? So we're creating 5 objects, okay. So you should imagine that when I run this, that we should see destructor is called a bunch of times, okay. Cool, does this make sense? Okay, so we created 5 objects, right? We can even see default constructor called for this final one right here. But only 4 objects are deleted. Okay, good. Okay, take a second. Explain to the person next to you, why are only 4 destructors called, even though we have created 5 objects? Okay, begin. Oh, hello? Okay, cool. Any volunteers? Why? Why are there only 4 destructors being called? Yeah. What was that? Oh, yes. Yeah, exactly. Because B4 was created on the heap. Sure. But why is the destructor not called for this, though? Yeah, we need to call delete, right? So what happens when you have a stack allocated member, stack allocated variable, is when you exit the scope, then all of these objects will be automatically cleaned up for you. This is just a nice benefit of working with things created on the stack. And this is maybe one of the biggest differences between developing for things on the stack versus on the heap. So yeah, in this case, all 4 of these objects are deleted. But anytime we use the keyword new, you always, no matter what, you always need to keep in the back of your mind, you always need to now delete the object. And the way you delete an object is you will take this before and you just type delete. Sorry, delete before. Okay, there we go. So that is all you need to do. And with this, now the destructor will be called. So let's go and run this. There we go. So now we can see 5 destructors called. Okay. If we didn't delete before, then this would be a memory leak, and maybe we were running our C++ program for like, I don't know, a few hours or something. Maybe we're playing like a video game or something, and if we had a memory leak, what would happen is our RAM usage would just start going up and up and up and up and up and up, and it would maybe after a while, like our game or our application would crash. So it's very important that we always delete any memory that we create. Yeah, question?
So is before, like if you don't delete it, is it a global variable or is it still like unaccessible?
So when you call new, anything that is allocated is, technically a global variable. It is accessible from anywhere, as long as you have a pointer to it, though. And in this case, we do have a pointer to it, but the second we actually leave the scope, then the pointer itself disappears. So we don't know like what integer value stores the address to this ball object. So yes, it's still a global variable, so technically, we could try to find it in our memory, but if we accidentally misstepped and if we grabbed the wrong address, then we would get a seg fault. Yeah. Cool. Also, kind of a funny thing. Does anyone know? There's probably multiple examples, but I'm thinking of a specific example. There's a Nintendo game that was so poorly optimized that there were like memory leaks everywhere. So instead of fixing the memory leaks, what they did is they just added more RAM to the game console. Does anyone know what game I'm talking about? Anyone know? This is Donkey Kong 64. So they created a whole separate RAM module that you plug into your Nintendo 64. And if you go and fix the memory leaks, you no longer need that extension. Kind of funny, yeah. What was that?
The disk drive?
Not the disk drive. There's an actual expansion, like RAM expansion pack. Anyways, funny stuff. Make sure you free all your variables. Yeah, cool. So let's go and fix this code up here that we wrote then, right? Because we're calling new. So anytime we construct an object, we call new. So what we need to make sure that we do is we need to call delete in our destructor. Okay, so so in here we can now call delete. And what are we deleting again in our destructor? Pointer, pointer, which is, this guy right here, pointer. Cool, delete pointer, good. Okay, there's also one other thing that we need to make sure that we do. So this assignment operator, is this a constructor? This is actually not a constructor, right? So when the memory is allocated for a ball, that is a constructor. But the operator overload, this is not a constructor. So what we need to make sure is, like here we're calling new int, but first we actually need to make sure that we clear out whatever value this pointer value was. So what we need to do is just call delete on this. Okay, cool, good, feeling okay? Okay, so let's go and test this, okay? Good, and it looks like things are working. And so there's this cool application called Valgrind. Has anyone heard of Valgrind? Okay, oh, this is incredible. Have you guys used Valgrind? You have. That's so cool. I will not show you Valgrind right now, but Valgrind is a cool application, as many of you know. It will help you analyze your C++ program. Especially, it will help you find memory leaks. It will help you see, like, are there any floating pointers anywhere? Like, is there any memory that doesn't have a pointer? Valgrind, really powerful. Instead, what I think maybe could be cooler is maybe let's go in and instead of adding this delete thing right here. So in theory, we should have now a memory leak. Let's just kind of benchmark our program for a second. So instead, what we can do is maybe create like a for loop. Int I equals 0. Okay. I is less than, maybe do like 10,000, or we could just do while true. That's probably better. So while true, right? Okay. And then we can do, ball b test. Let's make it a pointer equals new ball, and let's just call default constructor. And then maybe also let's b test 2, and then let's then call the assignment operator on this. Okay, and then we need to make sure that we then delete both objects here. Okay, so I just wrote this simple kind of benchmarking thing. I'll get rid of this line for a second. But now let's just see what happens. So right now, it's just going to, while true, it's just going to kind of run forever. Let's just make sure this works. Okay, good. So now it is running. It's running. Very exciting. Cool. So I'm now going to pull up my task manager, and did it just? That's weird. I guess you can't open it from VS Code. Okay, cool. So there we go. So we can see right here. So this is my WSL instance, And you can see that I'm pretty much staying exactly, like I'm not really allocating much more memory, right? It should be it's staying flat. So right now I'm using whatever, 20 gigabytes out of my 32, right? And we're good. However, if I now were to modify this and now add back this memory leak, right? Because I got rid of this delete pointer, so now like we're just going to be like deleting everything. In fact, maybe to just see it go faster, let's also get rid of this delete, right? Where is it? Delete in this destructor. And yeah, okay, this should be kind of nasty. So if I now go and kill this, how do you kill things in Unix? Control C, yeah. So I just ran Control C. Good, so now you see that it stops. Sometimes you have to press it a couple times. Okay, so now let's try running this, and great, okay, cool. So now I'm running it, and we should see that eventually memory should start going up. And you know, it might be better if I also get rid of all these print lines, because then it will also, each of those takes a long time to run. So, okay, let's do this. Okay, you ready for this? Okay, let's see. Okay, cool. So now it's allocating memory, and it's printing it out, and we can see, oh, look at this. Okay, it's sloping up. Even though I'm not like actually creating any memory, right? Like in theory, like I'm just running like new ball, and then I'm deleting ball, new ball, deleting ball, and then I have to kill this before my computer crashes. But there we go. And what's nice is when I kill it, okay, even though yes the memory was floating, well, the operating system keeps track of all the memory that it gave to this program, so the operating system now is able to clear up all of that memory. So you can see it starting to go back down. So it's okay in the long run that you have a memory leak, like it's not going to damage your computer, but it will mean that you can't run your application for a long time, because if you create a bunch of memory after like a few minutes, then now your program will probably crash. Yeah, question?
So why would you want to create, or what would the difference be between creating a ball on the heap and on the stack?
Sure. So the question was, why would you want to sometimes create a ball on the heap versus on the stack? So we came up with a couple reasons for why declaring things on the heap is better. Can anyone remind me? So what would be a benefit of creating things on the heap? Yeah. I would say that kind of goes for stack objects as well. Yeah. What does putting things on the heap give you? Yeah. Sure. Yeah.
I mean, there's more space on the heap, right?
Generally, yeah, there is more space on the heap. Yeah, so you have more room if you need to allocate a bunch of memory there. Another big thing is when you allocate things on the heap, you are able to specify the heap size dynamically. So if you were getting as user input maybe how much memory you need to allocate, then that would be a good application of putting things on the heap, because you can't really allocate a certain amount on the stack. In fact, what you would need to do is in stack memory, you would just like allocate 1,024 bytes total or something, and just hope that your user input won't exceed 1,024 bytes. That's what you would have to do on the stack. Yeah. And then the other reason is heap memory is all global. So that is also useful. Like if you want to ever leave a scope now, heap memory will stay persistent and won't disappear even after you've left that scope. Yeah. Cool. Yeah. Great question. Okay. Let's just really quick. Let's go and fix this memory leak. So if I fix that, so we should still see a little bit of a memory leak, but hopefully it shouldn't like slope up as aggressively. Okay. Let's see. Yeah. So we can see it's like starting to slope up a little bit. Right. Yeah. Cool. Okay. So let's go and fix that other memory leak now, which is this right here. Yeah. Okay, cool. Makes sense? Good. This is kind of a difficult thing. Like in this toy example, like kind of makes sense, right? Like if you create things on the heap, you just delete it. If you have an object that creates things on the heap, then in the destructor, you need to delete it. However, when you start dealing with like advanced kind of data structures, or if you have like a graph or something, things get very complicated very quickly. And so In fact, the US government has recently made a statement warning people about using C++, which is kind of funny. Has anyone seen this thing before? Yeah, kind of funny. Wait, I might have a link to it. Do I have a link to it? I had it. Let's see. Well, okay, I don't have a link to it. Let me see if I can pull it up really quick. Okay. Haha. No. Well, okay, this is so sad. I had the link, and now I've lost it. But anyways, I'll post it on Piazza. But yeah, the U.S. government actually released a statement that was like, please don't use C++ anymore. It's not memory safe, meaning that you are responsible for your own memory. Like anytime you create an object, you also need to be the one to delete the object. However, fortunately, C++ has added actually a memory-safe way of allocating to the heap. And this was a feature that was actually added like a while ago in C++11 and maybe 14. But yeah, and this is a probably more common way of creating heap memory now, with still all of the benefits of yeah, it's very large, and then also like can be dynamically sized, and then also being global. Cool. Has anyone heard of what this is? Yeah. Yeah. Unique pointer. What's the broader term that goes over unique pointer?
Smart pointers.
Smart pointers. Yeah. So there's this concept of smart pointers. There's several different types of smart pointers. But so let's quickly let's walk through a memory-safe way of dealing with heap memory. Cool. So yeah, let's create another one. Let's call it smart pointers. Okay. Yes. Okay. Cool. So for using smart pointers, we will need to do #include memory. Okay. And then we can do int main. Okay, and the way that you create a smart pointer, std, so the most common smart pointer is called a shared pointer. And a shared pointer is cool because you are able to use this pointer in like across several different like threads and objects and things, like as opposed to it being a unique pointer, which is just like one single instance of an object. So let's create this shared pointer. And in order to specify the type that we want to declare it in, we put it inside of these little brackets right here. We'll talk more about what these brackets are, but this means that it's a template, so we can like put in any type that we'd like, any type we'd like. We could put in like a ball type if we want, but in this case, we're just going to make an int, and I'll call this shared pointer 0 something. And then the way that you now allocate memory is you do, instead of new, instead you'll do std make shared. And we still need to specify that it's an int, and then here we specify the value that we want to declare it to. So let's just say make it the value 42. And so now we can take the shared pointer, and we can actually just use it like just as if it's regular pointer. So now we can like do std cout, and I can do this, and I can dereference it. Okay, and if I now turn 0, IO stream. Okay, let's go and compile this. Oops, that's okay. Okay. G++ smart pointer -o main. Okay, so now I've just run this, and so we can see that, so yeah, as I said, so I created this pointer, then I'm now printing out the value that was stored inside of this pointer, and then now we have the value 42 printed out. Cool. And yeah, notice that I'm not calling delete anywhere. Like I create this object, and I create it on the heap, but I don't have to call delete on this. And so this is memory safe. Okay. Yeah, and if we wanted, we could now maybe, if we wanted to reference this variable elsewhere, then we could Yeah, sure. We could create another shared pointer. I'll call this maybe shared pointer 1. Okay? And what we can do is just say shared pointer 1 equals now shared pointer 0. Okay? And this assignment is actually an overloaded assignment operator. You'll see that it actually does something extra special versus instead of just like this basic assignment. Because now what we can do is there's this really cool method that is called useCount. So I'm going to quickly print out the useCount of each of these. So I can take shared pointer 0, and I can do useCount, okay? And then I can do the same thing down there. So now I can print out shared pointer 0 and then shared pointer 1. There we go. So now when I run this, okay, so take a second, just by kind of what you think, kind of just reading through this. I know most of you probably haven't seen this before, but let me think for a second. What would you imagine will be printed out? What do you think this use count is? Okay. Turn to the person next to you, just like quickly whisper, be like, oh, I think it's going to print this. Okay, I'm going to run it. Okay. So there we go. So I just ran it. So now we see that it said 42, 1, then it said 42, 2, and 2. So what this use count is, it's actually really, really cool. So when you create a shared pointer, so when you do std make shared, what will happen is there will be an internal counter that is created for each pointer. And this counter is the number of times that that pointer is being used by something. So at the moment, right, so here we have created a shared pointer 1 that is like accessing the same memory as shared pointer 0. So therefore, the use count has gone up by 1. But now maybe if we wanted to now delete that value, but remember, so this shared pointer is actually, it's on the stack, like the pointer value itself, like the integer that points to where it is in memory, as well as the counter. So this value is stored on the stack. But if I now put it inside of this scope right here, right? Cool. So what will happen is when we enter this scope, then this object will be created. But then when I leave this scope, then this shared pointer, like the pointer itself, like the integer right here, this will be deleted. Okay. So now, turn to the person next to you and tell them now what you think will happen. Okay, cool. So let's see what happens. So let's see if you were right. Okay, enter. Okay, so cool. So we can see that it prints out 1, and then 2 and 2, and then at the end, because this object was deleted, now it's back down to 1. Okay. Okay. So what do you imagine now would happen when this shared pointer 0 is deleted, or like it is removed? So probably this counter, right, will start at like 1, and then I guess it goes up, then it goes back down. But then if we remove this if we remove the last pointer to this object that we created right here, this make shared object, if we lose access to this pointer, then now the use count will decrement to 0, so there's currently nothing looking at that object, and then now the memory will be cleared. So when this use count drops to 0, that is when the memory is destroyed. And this is done all automatically for you, so you don't need to worry about calling delete. And this is why unique pointers or shared pointers, smart pointers are so incredible, is now you don't have to worry about calling delete and you don't have to worry about memory leaks anymore. Instead, here's just this very basic kind of algorithm that just kind of works automatically. And yeah, so now your program is basically completely memory safe. Yeah, very cool. There is like one kind of small reason why maybe you wouldn't want to use a shared pointer. Okay. turn to the person next to you now and be like, hey, like I don't really like shared pointers because there's like one specific thing that is bad about them. So tell the person next to you what is bad about smart pointers. All right, begin. Okay, I'm seeing some like really fantastic discussions from maybe like a third of people, and then some people, I don't know. It's just helpful to collaborate and chat with people. Yeah, cool. So okay, any people, anyone who has an idea for why maybe shared pointers aren't always the best thing? Yeah.
Well, one issue is like cyclic references, where two objects can reference the same application and keep them alive permanently, so they never automatically deallocate.
I think that's fine. So the point was that you could have cyclic references to where maybe two objects are pointing at each other, and so they will never be deleted. Maybe you're thinking of an example that I'm not, but I don't necessarily see that as a problem, because if both objects are using the other object, then that probably sounds like they both deserve to still be around. But we can chat more if you have another idea. But okay, any other potential problems? Yeah. Exactly. There's more overhead. What types of overhead? Memory? Yeah. And then what's the other one? Well, it's slower as well, right? Because now every time that you create memory, now you need to increment this counter. I mean, granted, it's probably like one instruction. Like, it's not going to completely slow down your computer. But maybe if you're allocating a ton of memory, deallocating it, like if this is a very like frequent thing, if it's like in a very time-sensitive section of your code, then maybe you don't want to use smart pointers. And like if you're writing C++, there's a good chance that your code needs to be extremely performant. And so a lot of people, like, even though, you have smart pointers that are like really fast, a lot of people actually choose not to use smart pointers, because if they're choosing to write a program in C++, they're choosing to choose like the fastest language possible. And so they don't really, they don't see it being worth it to like increment this counter constantly. And then the other thing is memory overhead. Now we also have this counter value that we are having to deal with. Yeah. Okay, sure, cool. So that is shared pointers. Let me quickly just pull in this other version of it. It's kind of just like a little bit longer, but I just thought it'd be cool. I have this macro right here, which is nice. So I'm calling this macro print use code. So print use count. So I have up here hashtag define, and then print use count, and then here this is what it expands out to. Okay. Has anyone seen a macro before? Seen this? Okay, yeah, not as many. So this is a kind of a cool feature of C and C++. Really, actually, most C-like languages. So what we can do is it's kind of like declaring like a variable, except instead of a variable, it will auto-elaborate out into any expression that you want. So in this case, I'm saying anytime I ever, like later on in my code, type out this line, like type out this word, then please go and fill it out, like elaborate it out to this longer expression. Cool. So there we go. So that's what like that would do. Is it would be basically like printing that there. But this is just, I used this to kind of make the code a little cleaner. So here I have this make shared, and then I create a new pointer 1, then make a new pointer 2, and then here exit the scope, and then exit the scope. So we should see that it will probably, print out numbers incrementing then decrementing. Let's double check. Okay, so if I run this, and there we go. Use counts 1, 2, 3, and then 2, 1 with each decrement. There we go. And then it actually decrements one more time, but it decrements one more time as the program leaves the scope and as it decrements down to 0, then now the object is deleted. Cool. Smart pointers. You will absolutely need this for your final project. Okay. Cool. Okay. Good. So yeah, now I want to move on to more standard library things. So this is using the standard library. It's notated because you can tell it's standard library because it has this namespace resolution operator, which is this : so we're grabbing std : shared pointer. If this was maybe some other library, then it would probably have its own namespace associated with it. Instead, maybe you would see like JSON : or something, depending on whatever library that you pull in. In this case, we're pulling in the standard library, and so this is the shared pointer. The C++ standard library is really incredible and has so many features at your disposal. And we are going to be spending a lot of class going over, like a lot of this course, going over a lot of cool C++ standard library features. And the first thing that we're going to talk about are some containers or data structures. Okay, so have people used Python before? Okay, Python, right. In Python, you have lists, right? And when you have a list, you can like append things to lists. You can delete things from lists, right? Cool. So it turns out that Python lists are actually implemented the very similar way to a C++ object called a vector. Have people heard of vectors? Okay, good. So we're going to talk about vectors for a little bit. So I'm going to quickly create another file. For example, CPP. Okay, and the way that you, all right, please no yawning, thank you. Or at least yawn silently. Thank you. Okay, let's include vector. Oops. Sorry, just one sec. Okay. Okay, so now we've included vector. Now let's also include IOStream to print things out. Okay. So the way you create a vector is, so it's kind of similar to a shared pointer, to where you have to use the template syntax to define the type. So in this case, we can do std vector, and then we have to define the type. So let's define the type to be maybe character, okay? And then let's call it v. And then the way that you add things to vectors is you do v.pushback. And then in this, then we can say what we want to push back. So in this case, maybe we'll just push back in E. And then we can go and print out this member. If we want, we can do cout v.at0. This will give you the first element in this. Okay, people seen this? Okay, good. Good, so now we should see that we get this element E. Okay, so let's check this. Oops, sorry. Just thinking of something else. Okay. Okay, cool. Yeah, so we can see printed out E. That's good. So now let's go and push back some more things. And maybe instead of printing out at 0, I guess we could print out back. So now this will give us the last element, and then we could push back some more things. Oops. Okay, we'll just, I don't know, ETHAN. Okay. Good, there we go. So it prints out everything. And so this pushback feature right here. Okay, so when you have a contiguous bit of memory, what is really easy to do is just to add on like an extra element right on the back, right? If instead it was like push front, What we would need to do is we would need to insert it at the front and then push everything over, like by 1. And so what's nice is when we do this pushback function, this runs in constant time. So it doesn't matter like how big our vector is, no matter what, any time that we push back our element, it will just add a single element to the back, it'll just like allocate that memory, I guess, and then it will, just constant time, it's really great. If we instead did push front, then now that would need to like move everything over by 1. Okay, so that is the idea of pushback. However, that is not exactly how vectors work, right? Because we don't actually want to allocate memory like every single time another element is pushed back. So instead, what is a faster way of vectors, and this is how C++ has chosen to implement their vector standard library, is what you will do is you will allocate a bunch of memory all at once, and then when you do pushback, there's actually just an internal counter that just increments, that keeps track of whatever the size is of the current vector. So what we can do is instead of just looking at the last element, instead we could modify this to where we say maybe v.size. And so v.size gives us the size of like the number of things currently in the vector. So I'll call this size. Okay, and then here I can now call this the capacity. So the capacity is instead the total number of things that the vector element has already allocated for us. And so the way you get this is v.capacity. Okay, so now if I go and change all these out, it's fine. Okay, good. So what we should see is we should see the size going up by 1 every time, but the capacity probably shouldn't like change at all, right? Because the capacity is like it's just allocating a bunch of storage up front, and then we are incrementing the capacity. So this is a very common way of storing arrays of data. Okay, let's check this. Okay, so great, cool. So we can see that we start out with a size of 1 and capacity of 1. Okay, size of 2, capacity of 2. But then after that, then it says size 3, capacity 4, size 4, capacity 4, size 5, capacity 8. Okay, so, is this what you were expecting? It may be. Can you now chat with the person next to you? Why do we see this behavior? Really kind of look at it, let it sink in, and maybe think, what would happen now if I kept adding elements? What would the new capacity be as I just keep adding elements kind of forever and ever? What does this pattern kind of look like for you? Okay, cool. So, any volunteers? What do we imagine would happen? Actually, let's shout it out. So, right now the capacity you can see is at 8. So, what would happen to the capacity if we increased the size to 6? If we added one more element, shout out what the new capacity would be. 8. Okay. If we add one more element, what would the new capacity be? 8. Okay. If we added an 8th element, what would the capacity be? Probably still 8. Okay, but now the capacity is at 8, So we've achieved our maximum capacity, but if we now add one more element, then what do you think the new capacity will be? 16, yeah. Well, so what happens is every time the vector runs out of memory, now the total amount of memory will, like they've just decided that the best way to implement the pushback method is anytime you run out of memory, it will now allocate it'll allocate like double the amount of memory that it had before. And this turns out to be a really kind of useful strategy for keeping your amortized time complexity low. Kind of the issue, though, is actually the first thing that I told you about vectors. I told you that pushback actually runs in O of 1 time. Have people heard this concept, O of 1? That means constant time. It means that the size does not affect how long pushback takes. That's what I told you. Actually, that is not true. Instead, what happens is if you ever have the case where you need to reallocate a bunch more memory, then that act of reallocating will need to go through every single element in your array. And in this case, we only have 8 elements, not a big deal. But if we had maybe, 1 million elements in the array, and if, oh no, we ran out of space, then now our CPU is going to now need to copy over like 1 million elements from our array into a brand new vector of twice the size. Yeah. So therefore, pushback can actually be slow, because if you run out of capacity, then you need to allocate all that extra memory. And also, I will say, so when you allocate all that extra memory, so when you run out of capacity, what first happens, okay, maybe I'll quickly write this down. Okay, so when capacity is met, then first, double the capacity is allocated. It's allocated elsewhere. So using probably a new operator, like it creates new memory that's twice the size. Then it copies it over. Then it deletes the old memory. So this is a very kind of slow and laborious process. So ideally, you don't really want to have the opportunity for it to need to run this. It'd be nice if it would just, just always be an O of 1 insertion. Does anyone know what we can do in order to fix this and how to make sure that we never actually have this happen? Does anyone know? Okay. Did you know that we can avoid this problem? Okay. So we can avoid this with like very slow resizing if we call this method right here, which is v.reserve. And so what we can do is we could say reserve, 1,000 elements. And so now, if we rerun this example, then we can see the capacity is always at 1,000, and it no longer needs to do any memory allocations until finally, then when we try to push back the 1,001th element, then finally now it will need to do the process of allocating more memory and then deleting the old memory. So, cool. Okay. Question. Yeah, I was just thinking that. I'm not sure. I think it just doubles it. I don't think it does power of 2. I guess we could check it. I could say for I equals 0, I is less than 999, plus. And I could say pushback. Okay, and then I could run the rest of the code. So let's just see what happens. Okay, 999. Yep, so it looks like it doubles it, moves now to 2,000 instead of going to the power of 2. Yeah, cool. All right. Where did you all learn about big O notation? I heard like some people have heard this, right? Or all of you? Is this like a prerequisite for this course? Okay, great. Which class is it? 101? Okay, cool. Yeah, excellent. Do you know what amortized means? Like amortized time complexity? You hear about that? No? Okay. So that's slightly differently. So in this case, we would say that pushback is actually big O of n. Because in the worst case, or in like the worst possible case, pushback will need to allocate 2n memory and copy over n amount of memory. So yeah, so in the worst case, this is this O of n. But that will happen so rarely that we can effectively say that, well, it actually ends up only taking about like O of 1 time. So we kind of amortize it out. Amortize meaning like the average use case of this function is going to be O of 1. So the typical use case is going to be O of 1. But yes, occasionally it will like run really slow. So that's the idea of amortized. And that's a kind of important concept. So make sure that you have that in your study materials for any time that you're going into a job interview and someone's asking like, oh, like, can you explain to me what like the time complexity of pushback is? And you're like, oh, well, amortized, it's O of 1, but in the worst case, it's O of n. And their brain will be blown away. Like, great, hired. So amortized. Average. I would maybe call it the median time. Yeah. Cool. Okay. Good. So let me think. There's one final thing that I want to show you with vectors. Okay. So and this goes with a lot of containers. So so with containers, you have access to a bunch of really great C++ like standard library methods. And in fact, like one of them that we gain access to is sort. And so let me just quickly show you how to run sort. So in order to run sort, you will need to include from algorithm. Okay. And algorithm is this great kind of just library that when you include it, magically, like a lot of functionality will be given to you. And so let's see what happens now when we print out the array after we've sorted it. Let me also show you another syntax that maybe you've seen before. Not sure if it was covered. So if we wanted to print out all of the members in the array, first we want to iterate through them. So what I would do is do char, and I could say C, and then I can do a for each notation, which is this colon. Okay, anyone seen this? Yeah? No? Yeah, this is cool. Okay, so now I can print out everything that is inside of this array. Instead of size, I just want to do v at, no, I just want to do C. Yeah, that's right. So here I'm printing out this value, although I want to make sure that I print it as, no, this is fine, good, okay. So if I now print this, then we can see that it prints out Ethan, but if I now want to sort it, then this is how I sort it. So it's std sort, which comes from algorithm. Okay? And here I'm passing in v.begin and v.end. And effectively what these are is these are like pointers to the start of the array and pointer to the end of the array. So that as you go through, as sort goes through the array, it knows where to start and it knows where to stop. So now what I can do is I can now print this out. And there we go. Now it is sorted it. Yeah, cool. Okay, except this isn't quite a pointer. This is called, does anyone know what this is called? Anyone seen this? Huh? Yeah? 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 Yeah, this is called an iterator. So we will talk more about iterators in the next few classes. But yeah, so this is how you sort things using std vector. And if you ever wanted to sort like another data type, what's really nice is generally you can use this sort method across other data types. And if you wanted to write your own data type, you can even overload the like sorting function that it uses. And if you wanted, you can make it sort backwards, or you can make it sort depending on like your favorite letters or something. Yeah, so algorithm, it's really great. Standard library method. Yeah. Okay, cool. So I think that's kind of all I had planned for today. So any questions on anything? So yeah, make sure that you So smart pointers, very important. Make sure you remember them for your quiz that will be on Wednesday. There is no class on Friday. Today's Wednesday. Yeah, there's no class on Friday. Instead, I will publish a pre-recorded lecture that you will need to watch because there will be the quiz on Wednesday will cover something in that video. So make sure to watch the video that I release. Yeah, let me know if you have any questions. Hope you enjoy your 4-day weekend. Oh, yeah, questions. So also, I am posting all of the code on Canvas. It is at the moment, it's in the general C++ module. I don't think I'm 100% up to date. I will say that all of the lectures have now been posted to YouTube. So make sure that if you want to go through the lectures, you can see them on YouTube. I will post this lecture as soon as I can. Yeah, and I will also post today's code on Canvas as well. Maybe just double check. If you still can't see it, let me know and I can make a Piazza post about it. So, cool. Okay.